I'm Michael Lewis. I'm a local engineer. My background is embedded systems and motion control, and I'm also one of the mentors for ACME Robotics. And so I just wanted to give a plug at the beginning here that the organization that we compete through is actually called FIRST, and it's an international organization. It's one of the best STEM organizations that I'm aware of, really anywhere. My wife and I have been involved with a few STEM organizations, and this one is really, really good because not only does it teach the kids technology, but it also teaches them real-world situations and real-world pressures. And their competitions are very real-world events. I kind of do this because I wish it had been around when I was in college or when I was in high school. And so I think it's a great thing to pass on. And I would say that alum graduating from ACME, if they've applied themselves, probably have a level of knowledge of somewhere around a freshman or a sophomore in college at most engineering schools. So it's a huge boost, and not only in the engineering world, but also in business and marketing, et cetera. We have a lot of different roles on our team. These guys will talk about that a little bit more. So tonight, what we're going to talk about is we're going to introduce the team. We're going to tell you about ourselves, kind of our history, what we're doing, why we do it, and then we're going to talk about a couple of topics in robotics, and namely machine vision and motion profiling for motor control. And those are a little more in-depth, a little more technical for you technical people. And then after that, we're going to have Q&A. And then following that, Mike is going to talk a little bit about the future of the team. And then following that, hopefully we'll have the robot moving. We weren't really planning on moving the robot tonight, but we came here and saw lots of kids that wanted to see the robot move, so we did that. So the technical portions may be a little long for some of us. If you need to get up, then go wiggle. That's totally fine. Don't worry, you won't miss the robot moving. We'll make sure everybody gets back in time to see that. So introduce our speakers. This is Ryan Brott. He's our software lead. He's a senior at NU this year and grew up in Nevada County and is known by a few of you guys. Same Kelly Muir is also on our software team. Kelly actually wears a lot of hats. He is part of our business team, part of our mechanical design team, part of our software design team. He does many, many things for us. And he is a junior at NU this year, right?
Hi, I'm Ryan, and I'm, part of the software team on ACME. So, we're from ACME Robotics, a local high school competitive robotics team. And so, this is our 4th season competing. Kellen and I founded the team a few years ago in my basement. And since then, we've grown a lot. This year, we have 10 members, as pictured here. This was taken at our last competition on Saturday. And then we also have 4 mentors. Come on, from those early years. So yeah, and as Michael kind of mentioned, we compete through an organization called FIRST, which stands for Inspiration and Recognition of Science and Technology. And it was founded around 30 years ago by the famous serial entrepreneur and inventor, Dean Kamen. And so FIRST operates several robotics leagues. And so we're part of FIRST Tech Challenge. And so that's one of our high school level robotics leagues. And then below us, kind of aimed at middle schoolers, there's the FIRST Lego League. And so at that level, middle schoolers build robots using the Lego Mindstorms platform. And then kind of a step above us is the FIRST Robotics competition. And so that's still high school level, but just kind of bigger in every respect compared to our league. And so they're bigger robots, bigger fields. You can see over here, this is actually a match from an FRC game, and you can see it's much larger. We compete on a 12-foot by 12-foot arena, and this is more like basketball size. So,
as well as building and programming robots, there's lots of other stuff that happens in FTC. So it's the teams are kind of designed to function as like miniature startups. So we have to do lots of other things that would also be involved with that. We have to do all of our own fundraising, as we're not involved with any school. So that involves reaching out to local businesses and getting money. Also, we have to manage our budget. For example, before our previous competition, we ran into a little problem where we needed to get some more money in order to do the rebuild that we wanted to. And so, as well as managing that, we also have people doing lots of like marketing and outreach and creating our public image, as well as project management and more organizational stuff to make sure that the team functions smoothly. So there's lots of stuff just beyond robotics that FIRST teaches people, and that gets people involved in. So this is the game animation that first releases in September that every team sees and then builds a robot to compete with.
2 driver operators, a coach, and a robot. The robot must be built from materials specified in the game manual and fit within an 18-inch sizing cube. But after the match starts, it can expand. Each match is played with 4 randomly selected teams, 2 per alliance. Your alliance partner for one match may be your opponent in another. The game is played on a 12-foot square playing field with a foam tile floor and 1-foot-high walls. 2 red and 2 blue balancing stones are mounted on the field floor. 4 relics are positioned in the field corners. 4 jewel sets are positioned on the field walls. 4 crypto boxes are also located on the walls. In front of each crypto box is a taped-off safe zone. A glyph pit is also taped off in the center of the field. 24 gray and 24 brown glyphs are randomly arranged in the glyph pit. These foam blocks are 6 inches square. Red and blue relic recovery zones extend beyond the field toward the audience. And finally, the 2 alliance stations are taped off on opposite sides of the field. Prior to the start of the match, teams must balance their robots on the balancing stones. They can be in any orientation. Teams also preload 1 glyph per robot, selecting either color. Then, field personnel randomize the locations of the jewels. They also randomly select one of 3 pictograph designs and install them on the field walls. Each match begins with a 30-second autonomous period. During the autonomous period, there are a number of ways for teams to score, using only pre-programmed instructions. If only 1 jewel is left on the platform at the end of the autonomous period, the alliance corresponding to that color earns 30 points. Each glyph scored in a crypto box earns the alliance 15 points. The pictographs have coded messages indicating which of the crypto box columns is a key. If a robot can decode this message and place a glyph in the crypto box key, their alliance earns a 30-point bonus. Each robot parked in a safe zone earns their alliance 10 points. Following the autonomous period is the 2-minute driver-controlled period. There are a number of ways to score points. Each glyph scored in a crypto box earns the alliance 2 points. A completed row of glyphs earns an additional 10 points. And a completed column earns an additional 20 points. If an alliance can score 12 glyphs in one of the 6 cipher patterns, it will earn an additional 30 points. CryptoBox scores are cumulative and can add up quickly. The last 30 seconds of the driver-controlled period is the end game. If a team completes a CryptoBox cipher, they are allowed to place relics before the end game. During the end game, teams may reach over the perimeter wall and place a relic in the recovery zone to earn 10, 20, or 40 points. An upright relic earns an additional 15 points. And finally, each robot balanced on a balancing stone earns their alliance 20 points. There are many ways to score points in relic recovery, but there are also rules that, if not followed, will award points to your opponents. For example, a robot may not control more than 2 glyphs at a time. And robots may not place non-glyph elements into a crypto box. This has been a brief summary of the first relic recovery game. For complete rules, please read the entire game manual, and remember to check the Q&A forum.
After seeing this game video in September, we designed a robot to compete in this game and to score points with those various field elements. And so this and down there is the second iteration of the robot that we built to address this.
Okay, so now we've heard a little about the hardware. here's a little bit about how the control system and the electronics work. So at the core of the control system, there are 2 Android phones. One phone is called the driver station, and it attaches to the game pads, and that's what the drivers use to control the robot during the teleop period. And then that phone communicates wirelessly with a phone on the robot via Wi-Fi Direct. And then the robot controller phone, right, the phone on the robot, then connects via USB to an expansion hub, which then has peripherals to control motors and servos and sensors. And so we write software to run on the robot controller phone. And it's Android, so we use Java in Android Studio. And then we just send messages to the expansion hub to direct its actions as far as controlling motors and sensors and such. Okay, so now we're going to move in kind of the more technical portion. So I'm going to talk first about computer vision and how we use it to kind of help in this year's challenge. And then Kelly's going to talk a little bit about motion profiling. So to start off, kind of what is computer vision? It's basically gaining some kind of understanding of the environment from an image or video. And so there are various different kind of sub-areas in this big field of computer vision. And for our purposes, we're primarily concerned with object detection. And so here's kind of some motivation for why we decided to use vision this year. So the first thing is that during autonomous, it turns out localization is a very useful thing. So that's being able to tell the robot's position on the field. And that's kind of a precursor to being able to plan actions around like moving from point A to point B, right? And so a kind of simple approach to doing this pardon me, is using the encoders on the drive motors and the inertial measurement unit. So the drive encoders measure how many rotations the motors have rotated, and the inertial measurement unit gives us feedback as to the robot's orientation. And so by measuring how these quantities change over time, we can kind of maintain an estimate of the robot's position. So this works pretty well, although there's a drawback, which is that we tend to accumulate air over time. And in general, the more you move, the more air you will kind of accrue. And so usually you need some kind of other sensing technique to kind of rein in this air, right, and maybe at some points reset the air, right, so that it doesn't get out of control, right, because say in autonomous, if we're trying to have a multi-glyph autonomous where we're going to the crypto box and scoring glyphs and then going back to the glyph pit and taking more and then scoring, that's a lot of movement. And so over time, we'll accrue enough air so that we won't be able to effectively align and being able to score those glyphs properly. And so we need some kind of other sensing technique. And so normally you would use something like LiDAR or radar, although these aren't allowed by the competition. So we turn to vision. Another thing about, so vision this year is easy with the game elements because they're relatively simple. And by simple, I mean they're composed of like pretty well-defined saturated color blobs. And so we can kind of do more simplistic, primitive computer vision as opposed to more state-of-the-art advanced techniques like convolutional neural networks that you would need to detect more complex things like people or dogs or cats. And so here on the right, you can see a little animated GIF of a robot using its vision system to kind of track the goal, right? So as the robot moves, the turret in the center maintains, like it stares at the target. Okay, so a little about image representation. So we use the phones or the cameras on the Android phones to take pictures. And so once these pictures come into the software, they're represented as basically matrices. So if you imagine a grayscale image, that's composed of a bunch of little pixels, and each of those pixels kind of corresponds to a cell in this matrix, right, which represents the intensity of that pixel, right? So how white or how black it is, right, where it falls on the palette, right, over here on the right. And so then we can also use a similar technique to represent color images. And so this works by basically splitting the color into multiple components or channels. And so a common way of doing this is RGB, right? So you have one channel with the red intensities, one with the green intensities, one with the blue intensities. All right. So to kind of help us with implementing these computer vision pipelines and algorithms, we use an open source library called OpenCV. This is commonly used in industry, and it kind of provides implementations of basic computer vision operations, and then we use those at kind of a higher level and compose them to suit our specific use case, whether it's detecting the crypto box or joules or whatnot. All right, so before we move on to details about the various operations and how we can combine them, here's a very basic example for detecting the position of the joules. So if you recall from the game video, the joules are those little colored wiffle balls, right? There's one blue one, there's one red one, as you can kind of see here. And they're right next to the robot, right next to the balancing stone where the robot starts. And so one of the first tasks in Autonomous is to knock off the joule for the opposing alliance. And so to do that, since the joule position is randomized at the start of the match, you have to, we use vision to determine whether the joule on the left is red or blue, and then vice versa for the one on the right. And so we use vision, surprisingly. And since we know kind of that the robot is always in the same starting position, and the joule stand will always be in the same position, we know what regions in the image to look for the joules. And so in those kind of predefined regions, we sum the red and the blue channels and then use those values to determine which one is red and which one is blue. Okay, so now I'm going to go a little bit more into detail about some of the operations that OpenCV provides that we use. So the first one is pretty common outside of computer vision. It's just simple blurring, right? And so what this allows us to do is kind of remove noise and kind of smooth out the image before we have further processing steps. And so then after that, there's normally some kind of thresholding. And so thresholding takes kind of a grayscale image. So in a grayscale image, right, you can have anywhere from completely white to maybe half white, half black, right, some gray in the middle, any kind of shade of gray, right, and turns it into a binary one. So every pixel is either completely white or completely black. And so thresholding, you basically define a threshold, and any pixel that's lighter than that threshold becomes white, and anyone that's darker becomes black. And it's kind of a similar thing with color thresholding. You just do the same process for each channel, right? So if it's RGB, you'll do one for red, one for green, and one for blue. All right, so it turns out for color thresholding, it can be kind of annoying to determine thresholds for all three of the channels, and especially if the object you're trying to detect isn't either red, green, or blue. And so usually when we're doing color filtering in computer vision, we use an alternative color space. So that's just kind of a different way of representing colors called HSV. And so what HSV does is it kind of condenses all of the color information into one dimension, into one channel called the hue. And so that's what you use primarily for filtering. And then the saturation, the value encode the saturation and kind of the intensity of the color, which are usually less important than the hue. And so yeah, since the hue, we only really have to care about one dimension as opposed to 3 with RGB, we generally prefer HSV when doing color filtering. All right, so binary morphology. So this is just a fancy name for some very simple operations. It's kind of a family. And so the two basic ones are over here on the left. There's the dilate. So what the dilate does is it takes kind of the edges of your image and thickens them. And so you can here's the original image, and then here's the post-dilation result. And then the erosion does pretty much the exact opposite, right? Takes edges and thins them out. And so these two operations aren't really super useful by themselves, but it turns out by combining them, we can have more useful behavior. So for instance, a morphological open, which is an erode followed by a dilate. So what this does is it first does the erosion, and so you can see here the image is kind of noisy, right? We have our main contour that we're trying to detect, but there's some noise. And so what the erode does is for all of the major edges, it just kind of shrinks them, and all of the noise just completely goes away. And then the dilate's just there to kind of make the edge big again, right, back to its original size. And so that serves to remove a noise in the image. And then the close is kind of the reverse of an open. We first do a dilate and then an erode. So if you see here, there's some holes inside of our contour. So the dilate fills in those holes and makes the region bigger, and then the erode brings it back down to its original size. And so this is used for filling in holes in the various blobs in the image. And finally, contours. So this step basically takes a bunch of blobs, sorry, not color blobs, and finds kind of their boundary, a contour. And so this is kind of where we start to extract the useful information from the image, something that we can actually use for positioning or whatnot. And so say, for instance, you have an object that you're trying to detect with a known size. So then you can use the size of the contour in the image and some of the camera parameters to determine its distance from the camera. And there are several other ways to use these contour properties for similar purposes. Okay, so now let's put these all together. So this is a little bit more complicated pipeline for detecting the CryptoBox. And so it's primarily based on detecting the 4 rails, right? So you imagine the CryptoBox has 4 columns, right, that are either blue or red. And so up here in the top left, we have the original image. And so the first step we do is a little blur. And so that, of course, smooths the image and removes some noise initially. And then we do our HSV threshold to detect the blue. And so you see it picked up the major rails as well as a little bit of the balancing stone, although there is some noise. And so that's removed by the next step, the binary morphology. So here we first do a morphological open. So remember that removes noise. And then we do a morphological close to fill in these rail color blobs. And then finally we detect the contours. And then using this information, we're able to figure out where the rails are. And using the distance between the rails, we can tell how far the camera is from the CryptoBox. And then by the offset in the image of the CryptoBox rails, we can determine the offset of the CryptoBox from the camera. And so since the CryptoBox is always in a known position on the field, we can use this information to determine the robot's position at any given time. And so with this localization information, then we can use that to act, which is what Kelly's going to talk more about. All right. I don't know how this, yeah.
Okay. Okay, so now that we have this information, we have to act upon it. And like motion control and controlling motors on the robot in general kind of seems to be a rather simple task on face, but actually turns out to be surprisingly involved. So all of the subsystems on the robot, like the drive base, the arm that comes down to slap the jewel away, the lift that raises up our dump bed, all of these need to be controlled And in a competitive setting, making it as fast and accurate as possible is really advantageous. So having some sort of advanced motion control system can be a really big benefit to the team. So I guess before we can talk about like the specific way we use this, I'm going to talk about just control systems in general. And so use a control system anytime you have something and you want to get it from one state to another, from state A to state B, or you want to have it maintain a certain state and like maintain a certain target. And so this has lots of applications outside of just robotics and motion control. It's also used in industrial chemical processes where you're mixing or trying to control some reaction, or if you're having to control power supply to a power grid, or say you're trying to heat something at a certain temperature in an oven or a furnace or heating a house. And so the most common example probably comes in the form of the thermostat in your house. So this is pretty simple because the furnace will only have two states. It's either on or it's off. So a simple controller could, normally called like a bang-bang controller, would have it turn on the furnace if it falls below a certain temperature, say it's 72 degrees, and then turn off the furnace if it passes that. Of course, sometimes you'll have like a slightly larger window to prevent the furnace from flipping on and off really fast, but that's the general idea. But in practice, this sort of controller has lots of issues. So first, you can see here's the response graph. Here's the black is your target, and the green is what you actually get. And so this is a couple of problems. So first, you get a lot of overshoot around here as well as undershoot because the furnace and lots of systems take some time to cool down. After you stop applying the control, the furnace is still heating, or it still is releasing some hot air into the house, so you'll shoot past it. Similarly, when if it falls below your target and you turn it back on, it'll take some time to warm back up and resume heating, so you'll have lots of oscillation around the target. And so kind of a more refined version of this control is a PID controller. So a PID controller is a type of what's called a feedback controller, which means it works based on the error in the system. The error is the difference between where you want to be and where you actually are. And so it's comprised of three components. The first is a proportional component. Proportional component is meant to account for your current error, and it creates a proportional response to the current distance between where you are and where you want to be. This means that as you get further away from your target, it'll be a stronger response, and then it'll slow down as you reach your target. This makes sense for a lot of applications where it will minimize overshoot pretty well and prevent oscillation, because when you're around your target, you don't have the strong control that will cause you to fly past it. But in some instances, you need an integral component. This is when you have some constant force like gravity or friction acting on your system that will prevent a proportional component or a purely proportional controller from ever completely reaching it. In this case, you'll slowly build up a response to that constant force that will actually allow you to finally reach it. The problem with an integral component is what's called integral windup, where if you spend a long time away from your target, you'll have this big correction being placed even when you reach it, because it takes time for that integral component of tuning a PID controller, which means adjusting the gains of the three components to try to get the best response. So here you can see here's the beginning. So as you're turning up P, or the P gain, we get close, but not close enough because there's some constant force keeping us from getting there. So now we increase I. That means we'll actually get there, but there's a lot more oscillation because it takes time for the integral windup to go away. When we increase D, though, it will smooth everything out and dampen the whole thing, so now you have a fast and accurate response. The problem with this is when you apply it to motion, as we have to do with our robot, it has some issues. First of all, it won't observe the physical limitations of a mechanism, such as the maximum velocity or maximum acceleration that a component can safely undergo. So to resolve this, we use what's called motion profiling. This means this is a type of a feed forward as opposed to feedback control, which means that we're planning ahead and preemptively applying control to make sure that error doesn't arise in the first place. And so we generate basically a path to follow that will observe these physical limitations, such as the maximum velocity our drive base can reach, or the maximum acceleration some component can undergo. And then we also make sure that it's time optimal, because a PID controller, not tuned correctly, especially when applied to a moving component, might have lots of oscillations. That means it's actually taking you longer to reach your target. But by constructing a time-optimal motion profile and executing it accurately, we can be getting there a lot faster. And so one of the simplest type of motion profile is called a trapezoidal or acceleration-controlled motion profile. This means that we're limiting the maximum acceleration that the component can undergo. It has 3 sections here. So you have an acceleration phase, a cruising phase, and a deceleration phase, each with constant acceleration. And so this is pretty easy to generate. So first, we can calculate the maximum velocity that can be reached. This is either going to be the maximum velocity that we can reach before we overshoot our target, or the maximum velocity that our component can safely travel at, whichever is smaller. And then we determine how far we'll travel in the time that it will take us to accelerate and decelerate from this velocity, assuming we're accelerating at the maximum safe acceleration. From here, we calculate how much further we have to cruise in our cruise phase in order to reach our distance at the end of our deceleration phase. And then we calculate the durations for all of our segments. We have motion profile now. Now this can be executed and will get us there quickly and accurately. But the problem with this is that at these corners of the trapezoidal motion profile, it requires an instantaneous change in acceleration. So this, to resolve this, we use what's called a jerk-controlled motion profile or S-curve motion profile. So in the trapezoidal motion profile, when acceleration changes instantaneously, the derivative of acceleration, jerk, must be infinite. So this causes a lot of problems. But one, jerk, which you probably are all aware of as it's usually what people describe as jerky motion. It's why you slowly ease in on the accelerator or the brake when you're driving a car, because you don't want to apply all of the acceleration all the way at once. So when you are slamming on that, it will jostle your components a lot. This can be really hard on your mechanisms. It also lead to inaccuracies. If you're using dead reckoning localization, as Ryan talked about a little bit, that doesn't work if your wheels are slipping because you're applying acceleration too quickly. And so we have to construct a 7-segment motion profile where both the acceleration and deceleration phases actually consist of 3 phases themselves, one where you gradually apply acceleration, and then you gradually stop applying the acceleration, so everything is much smoother. So you can see here the difference between a trapezoidal or acceleration-controlled motion profile and a S-shaped or jerk-controlled motion profile, because when at the points of maximum jerk here, it actually causes a lot of backlash in the system that will cause the beer to fall out of the cup. And so, of course, there's also a problem with this. We're necessitating instantaneous changes in jerk. That means that at some points we have to make the derivative of jerk infinite. But it turns out that for our purposes, that the gains shown by going up to controlling the derivative of jerk are pretty negligible, and so we don't get any performance gains from doing that. But in some applications, people will go as far as using a 5th or 6th order controller, or using a trigonometric approximation of it to get even more precise movement, say for a medical application or something. And so now we have to put it all together. We have this motion profile, which is basically a 7-segment piecewise function that will describe where we should be, how fast we should be going, and how much we should be accelerating at any point during our travel. And so we want to integrate that into actually executing it. And so we have two different aspects of control here. We can combine the feed-forward aspect of motion profiling with a feedback aspect of PID. So first, we grab our set point. We're grabbing where we should be at that time for each time we update during this movement. There, we can figure out how fast we should be going and how much we need to be accelerating. This lets us determine a control to send to the motors, because as the motor kinematics work out, it's all proportional. So you can have a constant you multiply by both of those and you sum that, and that will get you most of the way. So if you're applying voltage to the motor that's proportional to your acceleration plus your velocity at each point, you'll get you almost all the way there. But there's always going to be some error in the system, because there might be a little bump in the road or something. And to this, we also add a PID controller or a feedback system. But instead of the usual feedback controller, where your error is the difference between where you are right now and where you eventually want to be, we grab where we want to be right now from the set point. from our motion profile. Now the error is a lot smaller, and the PID controller has to do a lot less work to ensure that we're on target and that we get there accurately. This also minimizes the problems associated with the PID controller, such as oscillation or integral windup. And so this means that we have our gains set a lot lower, and everything will be smoother as a result of that. So I guess we can open up to, so Mike is going to talk later about the team and the organization as a whole, but if there's any technical questions for me or Ryan, I think now would be the time for that.
Sixth grade, goes to First Legal League, goes to our league, First Tech Challenge, and then goes to FRC. So there are 4 different levels of competition all the way from K to 12. We chose to start at FTC. Actually, I started an FLL team at Penn Valley with my son 5 years ago. My son went to the high school. He's a senior this year, but he decided robotics wasn't his thing. I loved it so much, I stuck around and found Ryan and Kellen and Alicia, and we started the team 4 years ago. And now we've been able to recruit some excellent talent in Mike and Steph and a few other folks. So we're beginning to recruit to the local tech community. If any of you have an interest in being a mentor, this sounds fun to you, come talk to us, because our vision is big for the future. I'm working right now with Shivati on hopefully what will be a $40,000, $50,000 grant from FIRST on a STEM equity thread, which is trying to bring STEM to communities that are disadvantaged. And certainly they're trying to bring more kids of color and more girls into the program, but we qualify as a rural community because, again, I worked in the Bay Area for my entire career for various robotics companies, and I saw, we've been here for 12 years, and I saw what my peers had down there and we didn't have here. Cupertino High School, you guys all know about those type of things. And by the way, schools in the Bay Area at the next level that are sponsored by Google and Intel, they have $60,000 to $80,000 budgets. Right, so those kids have access to money and engineers and what have you, and so you can sort of see the inequity, and that's what we're going to pitch to try and get some grant. So my vision next fall is to try and get a First Lego team started at every elementary school here in Nevada County. One, so that these guys can have an experience, because imagine doing this with Legos. Legos means super simple, put it together. These guys already know how to build with Legos. And if you're intimidated by being a mentor, you don't have to be, because again, we're just here to keep these guys on task and getting things done. And the hardest thing that these guys don't understand is project management, right? Which is, hey, you know what, there's a tournament next Saturday, the robot has to work, right? So that's the biggest thing. The rest of it's all doing by learning. And we see just fantastic things happen when an idea is spawned, and we'll sort of wink our eyes and we're like, that's not really gonna work, but let's see where this goes. Right? And the kids do something that doesn't work, and that's where the aha moments happen, and that's where the learning happens, especially at Lego League, because man, parts can come apart and go back together in minutes, right? Try it. That's really what this is all about. So if this sounds interesting to you and you'd love to either come join us here, if we get the interest and grow, we'd love to start another FTC team as well. We think there's enough interest. 10 kids is about the limit that I think we can handle. If we get more interest, we're going to need to double or double again going forward. And same thing with at the elementary schools, the First Lego League. We look at that as the minor league. We want to get the kids interested. We want to, recruit from that. This last June, we had our first Lego camp using the Lego robotics, and we recruited 2 kids out of that program to our high school team. They were coming, actually one's in 7th and one's in 8th grade. So we took them younger kids because we saw the talent. So we scouted them and brought them up. So we have an ulterior motive in this, but the biggest motivation for us is just getting STEM and giving these kids an experience. Okay, so you guys ready to go?
Yep.
All right, so let's give you a demo now. So talk to any one of the mentors after interest in doing that. Now, this is what the McKenna wheels do. They can go in any direction. It just doesn't drive like a tank.
Okay.
Or a car.
Who wants to be first? Do you want to be first? Yeah, go talk to Kelly.
Just don't run it into the camera.
Okay. That one moves.
Intake is the
Okay, so this one moves it forward and back and side to side.
Yeah, we
This
don't
one
want to do
rotates.
robotics. I mean, this is a complete robotic program. But, that's a drinks skip.
And then this one also is type C.
We're doing graphics and classroom.
Oh yeah, yeah. In front of the robot, the stripes are in front of the robot too.
Right? That's all it takes. Yeah. Exactly. Each of the schools now are starting to build more STEM-based programs. So I know they're
Might try some early stage there.
I'm in Gilmore. Yeah. So I, again, I think
That was a full moon.
Yeah, that's fun, because that's
So, this right here is the robot, side to side and forward to back. And this one does
You know what you should
A little bit.
you know, the thing that's amazing is that my training days is this will be the
So, try to keep it over on the
I've seen, like we would do this probably only so it turns out